Welcome back to Tech Talk, everyone. Today we're diving into the world of self-driving cars, specifically the challenge of perception and forecasting how the world around a vehicle will evolve. Joining me is Ben Agro, one of the lead researchers behind a groundbreaking paper titled Unsupervised Occupancy Fields for Perception and Forecasting. Ben, thanks for joining us. Thanks for having me. It's great to be here. And we're also joined by a leading researcher in the field of robotics and AI. Thanks for lending your expertise.
My pleasure. It's always fascinating to see how AI is transforming the automotive world.
So Ben, let's start with the basics. Why is perception and forecasting so crucial for self-driving vehicles? Well, imagine you're driving a car. You need to constantly understand what's around you, pedestrians, other cars, obstacles, and anticipate how they might move. Self-driving systems face the same challenge, but with added complexities. They need to make accurate predictions to avoid collisions, navigate safely, and make smart decisions on the road. That's where perception and forecasting come in. Makes sense. And traditional approaches for perception and forecasting rely on supervised learning, right? That's correct. These methods usually involve training models on large datasets of labeled data, where each object in a scene has been identified and labeled, often with bounding boxes. Then the model learns to recognize and predict the motion of those objects. However, these approaches have some significant limitations. Can you elaborate on those limitations, Ben? Sure. First, labeling data is incredibly expensive and time-consuming. It requires human effort to meticulously identify every object in thousands of images or LiDAR scans. Second, these labeled datasets are typically limited to a predefined set of object categories. They might miss rare events or objects that haven't been explicitly labeled, which can be dangerous for autonomous systems. So what's the alternative? That's where your research, UNO, comes in, right? Exactly. UNO takes a different approach by employing unsupervised learning. Instead of relying on labeled data, we train a model to understand the world based on raw sensor data, specifically LiDAR data. Can you explain what you mean by occupancy fields and how they relate to LiDAR data, Ben? Think of it like this. LiDAR sensors emit laser beams that bounce off objects in the environment. The time it takes for the beam to return tells us the distance to the object. We can then represent this information as a 3D grid, where each cell indicates whether it's occupied or unoccupied. This grid is essentially an occupancy field. UNO leverages this raw LiDAR data to learn a continuous 4D, 3D space plus time representation of the world. So instead of relying on labeled objects, UNO learns to predict the occupancy of space over time based on the raw LiDAR data. Fascinating. Ben, can you walk us through the architecture of the UNO model? Sure. The model consists of two main components, a LiDAR encoder and an implicit occupancy decoder. The encoder takes a sequence of past LiDAR scans and transforms them into a 2D representation called a bird's eye view, BEV feature map. This feature map contains information about the scene in a way that's conducive to understanding object movement and dynamics. So the encoder essentially compresses the LiDAR information into a more useful format for the decoder. That's right. Then the decoder takes this BEV feature map and a set of query points in space and time. These query points are essentially requests for the model to predict whether the corresponding space is occupied or not. The decoder uses deformable attention to focus on relevant parts of the feature map and predict the occupancy probabilities at those query points. Deformable attention sounds complex. Can you break it down for us, Ben? Imagine you're looking at a photo of a crowded street. You want to focus on a particular person, maybe to predict their path. Deformable attention helps the model selectively focus on specific regions of the image that are most relevant to that task. In our case, it allows the decoder to attend to the most informative parts of the feature map to accurately predict occupancy. That's a great analogy. So how does UNO learn from this process? How is it trained? We train UNO using a self-supervised approach. This means we don't need explicit labels. We generate a set of query points from the future LiDAR data and use the occupancy implied by those points as supervision. For each query point, we know whether it's occupied or unoccupied based on the LiDAR returns, and we train the model to predict those occupancy labels accurately. We use a binary cross-entropy loss function to measure the difference between the model's predictions and the ground truth occupancy. That's fascinating, Ben. Doctor, from your perspective, what makes this approach so novel and potentially impactful?
What Ben and his team have done is truly remarkable. UNO breaks free from the limitations of supervised learning by effectively leveraging the raw LiDAR data itself as a form of self supervision. This has the potential to revolutionize the way we train perception and forecasting models for self driving systems. It opens the door to learning from far larger data sets without the need for expensive and time consuming labeling.
So, Ben, tell us about the key findings and results of your research. What were the major achievements? We tested UNO on three popular self-driving datasets: Argoverse 2, New Scenes, and Kitty. On point cloud forecasting, a task where the model predicts future LiDAR scans, UNO significantly outperformed existing unsupervised methods. It was particularly effective in capturing the movement and extent of dynamic objects. We also demonstrated that UNO can be easily transferred to the task of BV semantic occupancy forecasting, where the model predicts the occupancy of different object categories like vehicles, cyclists, and pedestrians. We found that UNO outperformed fully supervised methods, especially when trained on limited labeled data. This few-shot learning ability is crucial for real-world applications where labeled data might be scarce. That's really impressive, Ben. So what are the implications of these findings? How could they impact the development of self-driving systems? These findings suggest that UNO could significantly improve the robustness and safety of self-driving systems. It enables us to learn representations of the world from unlabeled data, which is far more readily available. This allows us to account for rare events and infrequent objects that are often missed in traditional, supervised approaches. Imagine a self-driving car encountering a construction zone with unfamiliar objects. UNO would be better equipped to handle such scenarios than a supervised model that has only seen common objects in its training data. That's a really important point, Ben. Doctor, what are your thoughts on the practical implications of these findings for the self-driving industry?
This research has the potential to significantly accelerate the development of safe and reliable self driving systems. By learning from unlabeled data, we can build models that are more resilient to unexpected situations and better prepared to handle real world complexities. This is a crucial step towards achieving the goal of widespread autonomous driving.
So Ben, while these results are exciting, are there any limitations or challenges that you encountered during your research? Certainly. One limitation is our reliance on calibrated sensor data. UNO assumes we know the exact position and orientation of the LiDAR sensors. In real-world scenarios, this information can be noisy or imprecise, which might affect the model's performance. We're also currently limited by the range and noise of LiDAR sensors. It's difficult to accurately predict occupancy at very long distances or in areas with high levels of noise. Finally, UNO has a tendency to hallucinate occupancy in regions that are far above the ego vehicle, as the LiDAR rays never reach those areas. We're actively working on addressing these limitations. So what are your plans for future research? Where do you see this research going from here? We're exploring a few promising avenues. One is to investigate the use of other sensor modalities, like cameras, to provide complementary information and improve the model's accuracy and robustness. We're also working on improving UNO's performance on rare and small objects, which are particularly challenging to perceive and forecast. We believe that by addressing these limitations, we can further enhance the capabilities of UNO and its potential to advance the field of autonomous perception. Doctor, what are your thoughts on potential future directions for this research, both within and beyond the realm of self-driving?
This research has far reaching implications beyond self driving. The ability to learn from unlabeled data opens the door to a wide range of applications in robotics, virtual reality, and even medical imaging. Imagine using UNO to create realistic virtual environments or to predict the behavior of cells in a microscopic image. The possibilities are truly endless. I'm excited to see how this research evolves and impacts the field of AI in the years to come.
Thanks for sharing your insights, Ben and Doctor. To sum things up, UNO is a significant breakthrough in the field of autonomous perception and forecasting. It offers a promising path towards building more robust and reliable self-driving systems by leveraging the power of unsupervised learning. We'll continue to follow the developments in this field and see how UNO contributes to a future with safer and more intelligent AI-powered systems. Thanks for listening, and be sure to tune in next week for more exciting discussions in the world of technology.